So, the next thing would be naturally is to look at reflection from a mirror. So, if you have a planar mirror, optical axis, incident light, reflected light, right? I am just going to give you the matrix now. It is 1 0 0 1. Height of course doesn't change, and the angle is also the same. You might think there might be some sign convention to worry about, but keep in mind that this is defined saying if the general travel of the ray is in one direction, we consider this as the general travel. That's the optical axis in this case. For the reflected ray, this is the optical axis. Okay, so always take the general direction of the ray into account. Okay, so that's my ray ABCD matrix for a planar mirror. You could of course carry out a similar operation as we did for refraction at a curved surface and work out for reflection at a curved surface, right? And it should be no surprise to you that if you do that, you will get, so this is the matrix for reflection at a curved mirror. Its matrix is going to be 1 0 1 2 by r, where r is the radius of curvature of the mirror. Now, I have given you an exercise to do sometime at the beginning, and I am very optimistic that you all have done it by now. Work out all the equations for a mirror, right? We worked out in the class imaging conditions for a lens and so on, and I had asked you to repeat that whole exercise for a mirror. So, if you have done that, you will know that the focal length of a mirror is given by 2 by r, sorry, the power of a mirror is given by 2 by r, right. So, it is not surprising that this matrix and this are really very similar, right. The C term, the term that changes the angle, is the only term of which has a value other than 1 or 0, right. Okay. So, we have looked at some standard matrices. We have also looked at how you would trace a ray through a system by cascading those matrices, and you can now see this is very powerful, very easy to do a calculation, to use a tool like MATLAB for example, and just give the ABCD parameters for an optical system with any number of elements in it, and you just need to take into account the matrix for every element, keeping in mind that travel through homogeneous medium requires an element to be treated as an element. Okay. So, we have some time, let us do an exercise which uses what you have learned and see it is not just that you can trace rays with this method, but you can also learn things about the system. You can use information, the fact that the A or the B or the C or the D parameter has a certain value, a specific value, or meets a certain condition means you can make a guess, or not a guess, you can estimate or you can make some knowledgeable informed decision about what is happening to the rays in the system. Okay. So, the exercise I want you to carry out is to find the cascaded matrix for this system. So, find the cascaded matrix for a ray that travels first through a distance d1, then through a lens of focal length f, and then through a distance d2. Okay. So, quickly do that matrix multiplication for me, keeping in mind that if this is associated with matrix M1, this with M2 and this with M3, you are going to have to do it in this order. So, I am basically asking you to find out M, where M is 1, D2, 0, 1, 1, 0, minus 1 by F, 1, 1, D1, 0, 1. I have arrived at this. Now, let us see if we can get some further information out of this. Let us take the case where 1 over D1 plus 1 over D2 is equal to 1 over F. What condition is this that I have imposed? It's the imaging condition, right? You saw it as 1 over U plus 1 over V is equal to F. Right? Now, let us say I say this happens to be true for this system. Now, if I could somehow apply this in this matrix that we have arrived at, can I get some information out of it? Now, D1 and D2 only both appear in the term B. So, let us pull out that term B, right, which is D1 minus D1 D2 by F plus D2, and I want to somehow impose this condition. So, if I take out D1 D2, I will have 1 over D2 minus 1 over F plus 1 over D1. And now, if I apply this condition, you can see that the term in the bracket is going to go to 0. So, for this particular case, the matrix M will reduce to 1 minus D2 by F minus 1 by F, 0, 1 minus D1 by, by F. What is this telling us? How does having the B coefficient, and now forget how I arrived at this, I am asking you, what is the significance of having the B coefficient as 0? What does that mean? What does it mean when you say an optical element or an optical operation has B equal to 0? What does that mean? B affects which parameter? Y2, right? Y2 is equal to AY1 plus B theta 1. And now we are saying B is 0. So, in effect we are saying we are removing this term always. Other words, A2 is equal to AY1. What does that mean? Irrespective of the angle coming in, the ray is going to some point, right? And we shouldn't be surprised, because if you look at this relationship, this is the imaging relationship. What does the imaging relationship tell us? Let's draw a figure. Let's say I had my optical axis, a lens, and I have an object, and I am tracing rays, let's say from the axial point. So, I am tracing rays, and if this object, and I am looking at the point where imaging is happening. Right? Irrespective of the angle of these rays, irrespective of theta 1, they all land up at this point. And that is what you expect for a good imaging system. All rays coming from one object point should arrive at the same image point. They should all have the same height. So, irrespective of theta 1, I can have an infinite set of rays, they each have a different theta 1. But if this is a good imaging system, they will all arrive at the same point in the image plane. I do not have to do on axis, I could look at this as I have an optical system and I have an object, and I am looking at all the rays coming from this point, and they all are getting, let's say it's imaged here. They are all getting imaged here. So, everything from this point is imaged here. They all have the same height y2. Irrespective of the angle. Okay. That information I have got from looking at the coefficients, or saying this particular coefficient is 0, what does it mean? Okay. We can look at one more thing before we end the class, and we can say, let's take the case where D2 is F. So, let's take a case, no, I am not considering the first case anymore. Let us say we take this case where D2 is F. That will make coefficient A go to 0, right? Now, what does that mean? If I have an optical system, I have a bunch of rays coming in, they all have different heights, but these different heights do not matter. They are all going to get focused at the focal distance. Okay, and maybe I can make it clearer if I do the on axis case, where I say all of these have different heights, but they all get focused to this point. Irrespective of the height of the ray, they will all reach this point here with a different angle. So, that is why this coefficient is not 0 here. So, they are all reaching this point here with a different angle, but it does not matter what height they come in. Right? And if I look at it, what does D2 equal to F say? You are saying the image plane is at the focal plane, and or that distance D2 is nothing but the focal distance, and in this particular case I am looking at rays coming in parallel. So, irrespective of the angle, they are all going to get focused to the focal plane. Okay. So, the idea in today's class was to show you that you can do ray tracing in a very simple manner using these matrix operations. You can arrive at a matrix for every optical operation. Standard optical operations may be a combination of matrices, and you need to carry that out once and get the combined matrix, and henceforth apply only the combined matrix. If you have a combined matrix for a system and you look at the places where A goes to 0 or B goes to 0 or C or D, you can learn something about the system. Right? Or you can say, if I apply this condition, this parameter goes to 0. So, under this condition, I will make it work like a good imaging system, or parallel rays will do this, so on. Right? So, it tells you a little bit of what you might need to do in order to make that optical system with that matrix behave in a certain way. Okay? That's all for today's class. Good morning. So, in yesterday's class, we looked at tracing rays using the matrix method, right? And we developed matrices for certain operations, and I gave you some as exercises. We also looked at how you can cascade various operations, and that in effect is the ray tracing procedure, because when you cascade matrices, you are in fact saying this is how the ray bends and travels through the optical system. So, we ended with a system shown here. I have gone back to yesterday's notes, and you see you have a lens. So, this system here, you have a lens with a distance before and after it, and we arrived at the matrix, the cascaded matrix for this system, which gave us this result over here. And then we said, let's apply a certain condition. We applied this condition 1 by d1 plus 1 by d2 is equal to 1 by f. Doing so turned one of these coefficients to 0. And we also looked at the implication. What does it mean if that coefficient is 0? right? So I want to go back to that, because though we looked at it, what exactly, it's important enough to take another look at this matrix. And we said when the coefficient b is 0, what does that imply? It means that any ray with height y1, this is a ray with height y1 at the object plane, right? It is going to get imaged at the image plane at y2, irrespective of the angle. That is what that b equal to 0 means. And that is the very definition of a good imaging system, right? If all rays from one object point get imaged to the same image point, that's a definition of a good imaging system, right? So we are saying all rays from y1, irrespective of theta 1 can have any value, they get imaged at y2. They may be coming to y2 with a different angle, but they are arriving at y2, and this is the definition of a good imaging system. So we can say that this matrix with coefficient b equal to 0, this gives us the conjugate points. This matrix that we developed in the last class was the matrix for a space, a lens, a space, and d1, d2 are conjugate points, and we know that now because b is equal to 0. Okay? Okay. Now, another thing you might not have noticed, but if you look at the matrices we developed yesterday, we did a matrix for travel through free space. So if you travel through the ray traveled through free space of distance d, this was the matrix that you got. The determinant of this matrix is 1. If you did the matrix for refraction, we had 1, 0, 0, n1 by n2, and the determinant of this matrix was n1 by n2, right? If you did the matrix for a lens, we had 1, 0, minus 1 by f1, so a lens of thin lens of focal length f. The matrix determinant of this matrix was 1. Okay, and if you go back to these derivations, wherever you had the determinant 1, we actually are getting that determinant because we made the assumption that the refractive index in the starting space, in the object space, and the refractive index in the image space were the same. In fact, we said it's n1, n2, n1, or air, n1, air, right? So if you go back to those derivations, and if you actually take your optical system, whatever it is, and then say I have n1 here and I have n2 here, the determinant of all of these matrices will end up being n1 by n2. Okay. So you can go back and verify that. Of course, with the refraction at a surface, because you have those two, you can't say same medium, because then you wouldn't have any refraction. So there the result comes automatically. But in other cases, if you do not pick the same medium for the object and the image space, you will end up as with a determinant which is a ratio of these two refractive indices. And this leads to a very powerful conservation law in optical systems. We aren't going to go into the details of it. You can derive this law using matrix methods, and maybe I'll give you an exercise in which you do that. But I want to mention the law because I want you to be familiar with it. Okay? So it gives rise to a powerful convention law. It has several names, conservation law. It has several names. It's very popularly known as the Lagrange invariant, or sometimes it's called the Lagrange-Helmholtz invariant. Okay? And if you use matrix techniques and this fact that the determinant always works out to be the ratio of the starting and the ending refractive indices, this law is going to look like this. So, invariant means something stays constant, and here it is as a ray travels through the system, something stays constant. Okay? And the constant turns out to be the product of these parameters. Let me make it clear what I mean by these parameters. So, again I have a lens, I am going to draw a thin lens, so I am drawing it as a line, and I have a ray traveling like this. And so, this is an axial ray. I have an object, this is y, this is alpha, I have an image, this is y dash, this is alpha dash, this is n dash, this is n. So, what is this constant? It is the product of the refractive index in that space, the angle that the axial ray makes with the optical axis, and the dimension of the field at that point. That stays same throughout the optical system. Okay? So, you can derive this using matrix methods. Where do you think this is going to be useful? So, you think about when we wanted to calculate magnification of a system. To calculate magnification, we always needed to find out the height we took the ratio of the heights at object and image. Right? So, you always have to find out location of the image, height of the image, where it is, and derive these parameters to get to magnification. Here, by tracing a single ray, I am able to get some information about the optical system. Just because there is a constant, say if I know something about this ray somewhere without having to figure out its something in object space, I am able to use this constant and find out parameters in image space. Okay? So, I will try to give you some exercises so you see the power of this law, but just be familiar with it. You might even see it in Oslo, they will give you some numbers saying this is the Lagrange invariant of your optical system. Okay? So, I just want you to be familiar with this.